Now, we're going to look at the question posed by one of your friends. I think this one is the first question being asked. Um, yeah, so we have this problem. Um, we have a card, a system here, 10 kilogram that release from rest when velocity is equal to 0, and there is no slack in the cable, mean there is no mechanical interference. So that will cause the system to lose its energy. That is the assumption that we made. With the spring arm stretch, right, when this system at rest, the spring is undeformed. The engine problem here is to determine the distance traveled by the 10 kilogram cart. So this is a cart, right? So this system have cart, we have pulley, we have this structure here, we have spring, we have some additional mesh, we have the cord, right? So there is a system. So but somehow this question a bit confusing. So I think the system here referring to the mechanical system here, I think. And the our inner problem is to determine the distance traveled by the 10 kilogram cart before it come to rest, right? Um, if the mass is approaching 0, we can declare the mass m, and when there is a fixed mass value of mass here, about 2 kilogram, right? Let us see some of the solution here in the book. um, this equation 3107, the first question answered will be 0.663 meters, and the second one will be 0.349 meters when the mass m is 2 kilogram. Basically, for uh, try to search in the book, right? So you can find the question is exactly what appear in the book, right? So the spring constant here is 125 Newton meters. Right. So this is a situation that we have. Right. Um, this is when the system consists of only a cord and a spring. The spring is uh, undeformed, and then we attach a coordinate system here, right? That's we give us the x and y coordinate system when we place the label here as a when at initial state, right? um, and the shoot angle is 25 degree with respect to the horizontal line. Similarly, when we place another mass here, m 2 kilogram mass, so we this mass is not cause the spring to deform yet. It's been held by some mechanisms, right? And our position vector for this location for the 10 kilogram card is uh, 0 along the s coordinate system, or 0 in I direction and 0 in Y direction. We're going to look at the, because the question refer to two kinematic state, so we're going to look at the first state when there is no mass here, right? So we try to get the position vectors and we label the final state as B, right? So here the angle for conversion, right, to convert the distance travels in x and y, because we want to calculate the potential energy changes and work done on the body by weight, for example, and by the external forces. So the angle will be 205. So we have 25 degree here. Here is the rules, a law, right, for the triangle, for the parallel lines. So we have 180 plus 25, which is 205, and the distance travel for this 10 kilo card is SB. So similarly, the string, the string also will travel for to SB, will stretch up to SB um, length, right? So from here we can get the SB along the S coordinate system is SB, and from I and J is minus 0.906 and 0.422 SB. And this is the active force diagram. Um, uh, because it's much more you can treat as a free body diagram, but in this case I just consider using the active force diagram, right? So we would like to know what is the component of force acting by weight, right? So I'm just using the S coordinate system, and the angle taken will be from here to there, right? So if T is 25 degree, right? This is 25 degree, and then this one will be 65 degree. So and this is in Newton, the weight W in newtons, and then we get the weight that act along the motion of the 10 kilogram card is 41.42 newtons, and those are normal to it if there is a friction, but in this case we're going to ignore the friction, so it's 88.82 newtons. And for the spring, here is the spring. We just ignore and then we consider it as external force acting on this active force diagram. So we have F, and it's always in negative of the tangential direction lah. So this is the motion of ini, and it's negative. So we assume that the mass is flowing this portion and then go to that direction. So so we have the summation of all forces acting on the mass 10 kilogram mass is uh, due to the component of weight in tangential direction minus the Fs, right? The spring force, right? Because this one is along the motion, this one is opposing the motion of the lead. So we get this one equal to ma, but here uh, because the system is at rest, so this one is 0, right? um, so from here we can find that we can get the value SP directly. So it's not only you can solve using the Newton's law, but you can also solve using the energy equation. But this one we're going to solve using the energy vector method. So this is the work in S coordinate system. So we have the net force. Um, this one is a workout when we want to use energy balance. I'm going to use energy balance, and I leave it to you to use the work energy method. So we have a dot scalar product for work. Uh, um, the work done by the system to bring to stretch the spring, right? So it's a half 125 newton meter square. The reason why we have negative here because we replace Fn with uh, uh, the amount of uh, because it's directed um, opposing the direction of the motion, so we have negative there. Yeah, really. Yes. So yeah, because this is the work done by the body to deform the spring, so we have negative there, right? um, so we can directly place it inside the energy balance. So this is the energy balance definition, and this is the definition of kinetic energy changes, potential energy changes, and this is the net amount of force uh, acting on the spring, right? So from that we can get the equation. So we just place in the equation, and finally this is a quadratic equation, and we can get the root of this equation, and we find that the card, 10 kilogram card, travel for up to 0.6663 meters. Now we go to the second state. So the second state, we add mass there, right? So now the distance travel will be SC. We are using the same coefficient matrix, um, and we find that the value of distance travels will be different because we have value of SC there, right? So this is the active force diagram. So from here we can find the summation of force that act in the tangential directions um, of this body, right, which consists of the mass as well as the force by the spring. So we have about 19.6 Newton plus 62.5 SC, right? This is spring. And then we can find that the force, the work done by the body to raise this uh, body M plus amount of energy that required to stretch the spring. So that's what we call a workout, right? Work done by the body to the surrounding. So from here we can reduce the equation. So we find that the same quadratic equation appear in this problem, and we can get the solution of the distance travel as C equal to 0.349. So I'm using root finders from XR junkie dot norm s finder as px in order for me to get the solution. So in order for us to know that the solution is realistic, with the mass we have a shorter distance compared to the cases when there is no mass attached to the spring.